Good afternoon, Year 12. Now, today we're going to be starting this little topic on transcription. It shouldn't take more than 10 or 15 minutes, I shouldn't think. Basically, just checking that you know how transcription works. Now, the kind of questions you'll see on this will be ranging from a 2 or 3 marker, asking you what some enzyme does, RNA polymerase or helicase, or up to a 6 marker where it says, describe the whole process of transcription. And by the end of the day, I would hope you would feel confident to answer that 6 marker, describe all the processes of transcription. Now, transcription and translation is the easier one, transcription, because it's very related to DNA replication. And if you know your DNA replication, and we'll end up doing one of these in DNA replication in the not too distant future, but if you know your DNA replication, this will be not too bad for you. So let's get started. We should know, transcription always starts with DNA. We're going to use this DNA to make mRNA. The mRNA is what we need to go and make a polypeptide chain of protein later on in translation. But we're going to need to make that mRNA using the DNA as a template. So here I have a piece of DNA, right? We've got your phosphate, your deoxyribose sugar, and your base making up a nucleotide. We've got loads of those forming one strand of DNA. And then you've got an anti-parallel piece of DNA going the other way. Anti-parallel, you say, well, we're looking here 5' to 3', meaning the phosphate sticks out the top of this piece of DNA. But on the other side, it's always the other way around. It's 3' to 5', with the phosphate sticking out the bottom. They're upside down relative to each other. It doesn't really matter, but you could be asked to describe how something being 5' or 3' affects an enzyme. We'll come to that some other time. So, regardless of that, we've got hydrogen bonds holding together the different bases in DNA, holding together the 2 strands. Now we're going to need to break those before we can do literally anything else with this DNA. Whether we want to replicate it, whether we want to transcribe it, we have to break those hydrogen bonds. And so just like in DNA replication, we have a helicase enzyme whose job is to move up several of those hydrogen bonds. Yeah, that's the power of my fantastic animation skill. You see, this is why I got ICT GCSE. So we've broken the hydrogen bonds, and you've got 2 separate strands of DNA. Now those 2 separate strands of DNA, they're going to float apart. Naturally, when you break the hydrogen bonds, they're going to be broken apart, and they're going to float a little way apart from each other. And they're actually held apart by other proteins, but it's completely outside of the A level, so let's not get onto that right now. Regardless, this piece of DNA is just going to float away, leaving behind what we call our template strand. Now, this is something people tend to forget when they describe the process of transcription. One of the marks in a transcription 6 marker will always be one strand is used as a template. You may say, why do I care? You care because you only get one piece of mRNA off of DNA, not 2, and because that is one of the major differences between this and DNA replication. Okay, so one strand is used as a template. I've picked this one on the left for what it's worth. Now, what's going to happen now is these guys, these bases up here, I point, if you can see what I'm doing, these bases here, the light blue things, they don't like to be on their own. They have little hydrogens and oxygens and carbons and nitrogens sticking out in all kinds of places which enable them to hydrogen bond with other things. And so they're going to naturally attract any other nucleotides in their vicinity. Now there are 3 RNA nucleotides hanging around in the nucleus. They're just hanging around, they're just doing their thing. And so if you leave these exposed, along will come some RNA nucleotides. Alright? Along will come some RNA nucleotides. And they bond on using hydrogen bonds, right? So we're going to form some hydrogen bonds with these RNA nucleotides. Fine. So now we've got some DNA here. This is our original DNA strand, and we've got some RNA nucleotides bound on. Now you'll immediately see again, thanks to my powerful Photoshop skills, this T is not a T anymore, it's a U. That's how I know it's an RNA nucleotide, because it has uracil and not thymine, amongst other reasons. It doesn't have deoxyribose as ribose, for instance. Now, that's all very well and good, but if you imagine me breaking these hydrogen bonds right now, as I will in a minute, what's going to happen? Well, all these nucleotides are just going to float away. This is not a piece of RNA yet. Why not? Well, because I need to join these nucleotides together to form a chain. Right now it's just a load of nucleotides. I've got to join them together. So along will come an enzyme called RNA polymerase. And RNA polymerase's only job is to join together these nucleotides. And when he does, actually that's a lie. When you get to degree, you'll realise that's a lie. But at A level, its only job is to join together the nucleotides. He's going to move up and he's going to form phosphodiester bonds between the phosphates and the sugars. So now I've got a chain of RNA nucleotides joined together. Now this is another mistake people commonly make. They say we are joining the nucleotides together using RNA polymerase. That is not true. We are not joining the nucleotides together. Instead, we are joining, we are not joining the bases together. Instead, we are joining the nucleotides together. So we are not joining the bases together, we're joining the nucleotides together. And people write that we are joining the bases together. So if we were joining the bases together, well, there's only two things that can mean. We're either joining this base to this base, that's already happened, that's a hydrogen bond. Or we're joining this base to this base, that never happens, that's not a thing. We are not joining bases together, we are joining nucleotides together. Now you may say, why am I focusing on this? Because maybe a third of the year will always write that we join the bases together using RNA polymerase, and you should not be that person because that's incorrect. We're joining the nucleotides together, or, going to be even more specific, we're joining a phosphate to a sugar. We're joining a phosphate to a ribose sugar. Fine. And these black lines here, they're phosphodiester bonds, for what it's worth. Now, this will then just float away. So this piece of RNA here will now float away. These hydrogen bonds are very transitory. They can be easily broken apart. The RNA will float away and it will do its own thing. It will become a piece of RNA. And the DNA will reform into its original lovely DNA double helix. Now there's one more stage, and this is the final stage people tend to forget, and that is about splicing. So if you are a eukaryote, you have introns. Introns, the way I remember that it's introns and not exons that are these, introns are interruptions. They're interruptions in the coding DNA. So introns are interruptions. We need them removed. We need them gone. They don't code for anything. They are non-coding DNA, so they need to be gone. So we have to cut them out using various endonuclease enzymes. Enzymes to cut out these introns. So the final bit is to say, at the end of these long process of making RNA, we need to splice the RNA. We need to remove the introns. We need to make mature mRNA or just mRNA. Fine. From the beginning then, one more time. All the way back to the top. Helicase breaks the hydrogen bonds. Bam. It then goes away and does this thing. One piece of DNA then floats away. These guys don't like to be alone. The nucleotide bases, these bases don't like to be alone. So RNA nucleotides come along and they say, we'll be your friends, we'll join up with you, we like you. Okay, so along they come, they join up. Complementary base pairing. A to U, T to A, G to C, C to G. And they join using hydrogen bonds. But they're not good enough yet. We need to join the nucleotides together, so along comes RNA polymerase. RNA polymerase zooms up and joins the nucleotides together with phosphodiester bonds. That mRNA will then float away because these hydrogen bonds will naturally break. It then goes away and it looks a bit like this. And the exons need to be cut. The introns, need to be cut out using endonuclease enzymes. This is called splicing, and that produces mature mRNA. So, here's mistakes people make. I've already gone through them. Forgetting to mention there's only one template strand is a classic. Saying RNA polymerase joins the bases together, that's just wrong. And forgetting to mention splicing if it's required. Some questions will specifically say do not include splicing because they don't want to have a mark for that, but most won't. So, to finish off then, 6 marks here. I'd like you to try to bullet point this. Now you may have been taking notes as you went along, in which case there's no need to write a full answer. If you weren't taking notes as you went along, write this out in full so that you have some notes, some revision notes. 6 marks, pause me, do the question, I'll go through the answer in whatever time it takes you, 5-6 minutes. Fine. The answers then. 1 mark for saying the word helicase. You get a mark just for mentioning the word helicase. That's not bad. Breaks the hydrogen bonds. If you said unwound double helix, people do write that. It's another fairly common mistake, not a ridiculous thing. If you say that, you won't get a mark. It's not specific enough. It's breaking the hydrogen bonds. One strand used as a template. Don't forget to write it. RNA nucleotides attracted to DNA by complementary base pairing rule. You cannot just say nucleotides. You have to say RNA nucleotides. If you say the word nucleotide, you really usually mean DNA nucleotides. These are RNA nucleotides specifically. Complementary base pairing rule. Instead, you could write A to U, T to A, C to G, G to C. I just think it's quicker to write complementary base pairing. RNA polymerase joins RNA nucleotides together. RNA splice to remove introns. Right. If you didn't get 6 marks there, if you think it will be helpful to you, go and rewatch the video, particularly the bit you got wrong. Or if you found the video not helpful, at the very least, this should show you what you don't know. Go to a textbook, go to online, find some way of memorizing this, because it will come up again. I have absolutely no doubt. Fine. Hopefully you feel a bit more confident about transcription by the end of this. And I look forward to seeing you all in school at some point in the near future. Thank you.